Alrighty, IB Chemers, here is a video on 5.3. So just the big picture stuff I want you to focus on for this one is really looking at, first of all, this idea of, where does this energy come from, right? It takes energy to break bonds, right? You have to pull them apart. It's hard to do. But when you form bonds, you're doing that because it makes things more stable. Therefore, they release energy, right? So that basic idea and understanding of it, you needing to take in energy while breaking bonds, and that you release energy when forming bonds. And then also just recognizing that all bonds are not created equal, okay? And we'll see that in this section. And then also recognizing this word average here. This is super duper duper important. That is the key thing about bond enthalpies, is that they are averaged values, and they are that average of all sorts of different environments that specific bond is living in, right? And so none of those values will ever be exact. And then, calculating and moving forward. So that's pretty much it. But then also remember that here is where you need to focus on ozone. I'll have you do a little deep dive into that for sure, because it's a very common example and it's an important one to understand. So the things I want to go over real quick, and honestly, this is going to dip into 5.2 a little bit as well, but not the part that I don't want us looking at yet. So essentially, you already read about this idea of enthalpy of reaction, right? How much energy is involved in a chemical reaction. Well, where do those numbers come from, right? We can get them through experimental methods like calorimetry, right? We're going to do some chemical calorimetry in our next lab, where you do a reaction and measure that heat change just like what you did with your metals, but now we're looking at a chemical reaction. So we could get that experimentally. Probably you all have seen some issues around the validity and the quality of that data, but that's okay. But then we can also calculate it from theoretical values. So there's two different kinds of theoretical values that we're going to look at, and those are enthalpy of formation and average bond enthalpy. And so enthalpy of formation is looking at the energy involved in forming that compound from its bonds in their standard states, right? This definition right here is important. The IB really cares that you know about your definitions. And then also really recognizing that all the time we're talking about a per mole sort of a situation here. So if you want to form a compound from the elements, you have to, if they're diatomic elements, you have to break them apart. But then other than that, you're just putting atoms together. So often I would predict that those values would generally be exothermic. They would generally be negative values because you're forming things, right, from plain elements. But keep in mind, they won't be if you are starting with a diatomic, because you have to break that diatomic apart. So you'll see that, and I just don't want you to get confused by it. Then, and this is the part that we really look at in 5.3 specifically, is this average bond enthalpy piece. And so this is where you look at every little bond in the molecule that is being broken and every little bond that is being formed, and look at how much energy that takes. And those values are experimentally obtained, but rigorously, and then averaged from a bunch of different molecules that all have, say, a CH bond or an OO bond or whatever, right? So they have all these average values for the strength of those bonds based on, the energetics of breaking them. So that's what you're looking at there. But the one big thing I want you to understand, whichever of these two methods that you use, is the following. This guy right here, okay? Add up all the energy in and out of the reaction. I don't care what method you're using if you're doing this theoretically, right? If you're using enthalpy of formation data, fine. If you're using bond enthalpy data, fine. If you're later doing Hess's law and use, combustion data in there as well, great. Doesn't matter what data you're using, as long as you're making sure that you are adding up all the energy in and out of the reaction and recognizing the limitations of the data that you're using, okay? So that's the idea. So just a quick peek with the enthalpy of formation, right? In general, we are looking at, let's not do that yet, right? We are looking at reactants becoming products, right? So the reactants, we know for a chemical reaction, they're going to break apart, right? It's the products that are going to be forming. So if this value is an enthalpy of formation, right? They are forming, right? So these are called what I would call forming values, right? So you can only use them as written when you are forming those bonds, right? Over here on that product side. When you're breaking the bonds, you're doing the opposite thing. But the super cool thing about thermochem is as long as you're doing the opposite thing and it's perfectly opposite, all you have to do is reverse the sign. Okay, because those values, they're not breaking. They're not forming. I'm sorry, they're breaking. You're pulling apart the reactants. So you can't say they're forming, but they are doing the exact opposite process of forming. Therefore, you can use that value in reverse, right? These values of the enthalpy of reaction and so forth, they're state functions. It doesn't matter how you get there. It matters that you get there. So if you're starting from one thing and going to the other thing and it's the same process, it's the same amount of energy. Just that's the deal, right? It can't disappear. It can't show up from nowhere. That's the way it goes. All right, so then when we look at bond enthalpies, it's actually a very different thing because, right, thinking about average bond enthalpy, like how do we get those? Well, they are from the breaking of bonds, right? So these are actually breaking values because that is how we get those numbers, right? Which means they are only true, right? When we look at them on a data table, they are only true for things that are breaking, right? So when we look at our reactants, well, then those we will, oopsie, that's not what I wanted to do, I'm sorry, right? We will use those values as is, no problem, right? But now when we're forming our products, now we have to, if we're using bond enthalpies, we have to reverse the sign here, okay? So it's kind of opposite for the two different reactions. There's an equation that the book will give you, and I really hate that they do because you have to remember which equation do I use, and there's one for this, but one of them you add and one of them you subtract, and and I just really recommend you think about it this way instead. You just think about, I'm adding up all the energy in and out of the reaction. I have this data I can use, and I understand where it came from. I understand how to use it, right? If it's an enthalpy of formation value, the value is for the forming of that thing. So if it's breaking, I can still use the number, but I have to reverse the sign. Okay? All right, so then, oh, no. Oh goodness, is it gonna not let me? Let me move the thing. Oh, that's a shame. I have examples there. Hang on, let's see if I can make this happen. Oh, no, that's not what I want. This is what I want. All right, guys, I'll get you there. I'm sorry. Just maybe delete that. There we go. Oh, there we go. Yes, good. Let's do this one. And I'll just delete that. Okay, so my little notes there, right? So flip the sign on your enthalpy of formation values when they're breaking, right? When you are using them for reactants. For bond enthalpy values, you flip the sign on those products, okay? And then, yes, I have a little example here. So here are two examples, right, thinking about the combustion of ethane. So if we're using our enthalpy of formation values, right, the values that we are using, just for example, are going to be, right, the values that take carbon and H2, right, and that would be what, carbon probably solid and H2 gas, to turn them into C2H6 gas. And you would have to look that up, and that value would have to exist somewhere, right? But that's that enthalpy of formation value. If we were looking at oxygen, right, it would be the formation of O2. Wait a minute. O2 doesn't form, O2 just is. So what are we going to do there? Nothing, right? Pure elements have an enthalpy of formation value of 0 because they just exist. They just are, right? But right, for CO2, it would be carbon plus oxygen, that'd be the solid, that'd be the gas, to make CO2 gas. And again, you would look that value up. But when looking it up, all you're doing is looking for the thing that is forming because that's, how they're listed, okay? Then we can think about using bond enthalpies, right? And that is a different thing because for bond enthalpies, we are then going to look and go, okay, what's going on with the bonds? So you have two options with bond enthalpies. You can do the extra work or not extra work. If you want to do extra work, you can write down and add up all of the bonds in the reactants, and then also on the other side, add up all of the bonds in the products, and then, get rid of, right, you're using bond enthalpies. It's for breaking, reactants are breaking. So flip the sign on the products, add them all together, and you'll get the right answer. However, recognize that only some of these bonds are breaking and some of these bonds are forming, right? So maybe you don't have to do all that work. I guess, we're making I'm lying to you now because we're making water and carbon dioxide from burning stuff. So yes, all of these things get broken apart. But normal reactions that aren't combustion, you don't have to do all that work. You can just look at specifically what is breaking and what is forming, and that becomes a lot more useful. But anyways, so looking at this, right, we're going to say, okay, if our molecule, and I'll just redraw it here, is this guy, right, what bonds do I have? Well, I'm going to have a carbon-carbon bond, right? That's my right here guy. And then I'm also going to have 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds, right? And I'm going to have to find the values for those again in a data table, add it up, and put it out there. Okay. So if we, dang it, fine. Okay, let me get rid of all this real quick. And I just want to show you the math, and then I'm going to kill this video because it's taking way too long. And I do not want you to have to sit here watching this forever. Kill that, and kill that. Okay, so here's the math for these two things. And what you end up seeing, I don't know what those black numbers are, so ignore those for now. I don't know what the black numbers are. We can look at this in class if you want. But anyways, this is the idea. This is the kind of data you would get. You would get it from your data booklet. This is how you would plug it in. And you're going to either take, you know, this idea of products minus reactants, which I think is silly, or you're going to just opposite, you know, reverse some of those values. And for here, right, I took my bond enthalpies, and these are my breaking, right? So I'm leaving those the way they are. These are my forming, and so I'm reversing the sign, right? Forming, right there is my reversing the sign. Right? And up here, right, these are my enthalpy of formations. Oh, and I didn't take good notes for you, I'm sorry. But I am guessing that, oh, which one is probably which? This one, I must have done them in order. Oh yeah, because that's a 1. Okay, great. So this is going to be, you know, a breaking, right? This is going to be a forming, and this is going to be a forming. And so here, right, there is my reverse of the sign. Okay, so that's the idea there. We can talk about it more in class. See ya.